Congratulations, everyone. You've made it through to the end of the course. So we worked quite hard in 6.2 and 6.3 to understand how to find volumes using slicing and cylindrical shells. And now in 6.5, we're going to wrap it up with a pretty easy section looking at how to find the average value of a function. And we're all familiar with how to find the average value of a finite bunch of numbers. Say if I have 10 numbers and I want to find the average, I would add them all up and divide by 10. Or if I have 100 numbers, I would add them all up and divide by 100, right? We add the numbers and then we divide by the number of numbers that we added. That will give us the average value. But what do we mean by the average value of an infinite amount of numbers, or the average value of a function, say, on an interval? So let's see how it works. And basically the definition is the following. So if we have a function on AB, which is integrable, meaning that we can calculate the integral as usual. So all the functions we see in this course are going to be integrable. To find the average value, all we have to do is integrate from A to B using fundamental theorem of calculus, and then divide by B minus A. So finding the average value is almost the same as finding the integral. The only extra step is that we have to divide by the length of the interval. So dividing by B minus A. So why is it this formula? It comes about, as you could guess, by chopping AB up into a bunch of little pieces. We pick a sample point from each piece. We find the function value, and then we average all those function values. We get a number which somehow is an approximation of the average, and then we take a limit as we chop up into more and more pieces, and we take the average of more and more numbers, right? So we say chop into 5 pieces. We take the average value of five values. That gives us an approximation. We chop the interval up into 100 pieces. We take the average of 100 different values of the function. That gives us a better approximation, and so on. We take the limit. We get this average value. We just integrate and divide by the length of the interval. So I'm going to skip all over that because it's the same as we've always been doing when we're deriving formulas with integrals. Okay, another way of thinking about average value is if we multiply both sides of this equation by b minus a, we get the integral of f is equal to the average value times b minus a. On the left, the integral is the area under the curve, and on the right, there is a product, which is the area of a rectangle, which has base AB, so the width is b minus a, and the height is the average value. So in other words, that's saying that if we take AB, our interval, as our base, and we draw a rectangle whose height is the average value, then the area of that rectangle is the same as the area under the curve. So the area under the rectangle whose height is the average value is the same as the area under the curve. It's just a geometric way of thinking about things. Okay, let's see an example where we actually calculate the average value. For instance, let's try to find the average value of 3 cosine x on minus pi over 2 to pi over 2. Okay, pretty typical example. We're given a function, we're given an interval, we have everything we need. We just use that average value formula. We have to do 1 over b minus a times the integral. So here we have 1 over, and then b minus a is going to be pi over 2 minus pi over 2. So it's pi over 2 plus pi over 2. So b minus a is going to be pi. So we have 1 over b minus a is 1 over pi. And then we just have to integrate our function over our interval. So 3 cosine x from minus pi over 2 to pi over 2. Okay, use fundamental theorem of calculus, find the antiderivative, which is 3 sine x, plug in the endpoints. We get 2 after we subtract them. So we have 2 times 10 times 3, which gives us 6 divided by pi. So the answer is 6 divided by pi. Okay, so if you're ever asked to find the average value of a function on an interval, it should be dead easy. Just remember the definition, integrate and divide by the length of the interval. Okay, the last thing we have to understand is the mean value theorem for integrals. That says that if f is continuous on an interval AB, then there exists a point in AB such that the average value of the function, so that the value of the function is equal to the average value. So at some point, the function takes its average value. And this makes sense for continuous functions. Say, for instance, if you're driving somewhere, at some point you'll be driving, say your average speed is, say, 30 miles per hour. At some time you'll be driving 40, at some time you'll be driving 20. Well, if you're ever going to get from 20 miles per hour to 40 miles per hour, you're going to pass through 30 miles per hour in the middle, right? Sometimes you'll be bigger than the average, sometimes you'll be smaller than the average. Okay, if your function is continuous, then at some point you will also pass through the average. So this makes sense also from a physical intuitive point of view. And why is it called the mean value theorem for integrals? Just remember that the average value is an integral. So it's a theorem about average values, but the average value in this case was an integral, so that's why it's called mean value theorem for integrals. Okay, so at some point, the function value equals the average value. It doesn't tell us what C is, just like in the regular mean value theorem with derivatives, that doesn't tell us what C is, it just tells us C exists, it has some property. Here it's the same story, right? There exists a C so that the function value is equal to the average value. It doesn't tell us what the value of C is. Okay, so let's see one example where we're applying this. So let's consider f of x equals 1 over x on 1 to 3. So we have a function, we have our interval, find all values of c for which the mean value theorem for integrals holds. Okay, so in other words, we're solving the equation f of c equals the average value of c. So we want to figure out what the c are. So the mean value theorem for integrals does not tell us those, so the only way to find those is to solve the equation ourselves by hand. So let's first calculate the average value. That's going to be a number. So we have to do 1 over b minus a, which in this case is 1 over 3 minus 1, so 1 over 2, times the integral of our function on our interval, so the integral from 1 to 3 of 1 over x. So if we do the antiderivative, that's going to be L in absolute value x. We plug in 3, we get ln 3. We plug in 1, ln 1 is 0, so we're left with ln 3. And then we have the half hanging out, so we're going to get a half ln 3. So our average value of our function is a half ln 3. And now we want to go back to solving our equation. So f of c equals the average value, so it equals a half ln 3. And f of c here, if we use our formula, f of x is 1 over x, so f of c is 1 over c. So in other words, we're solving 1 over c equals a half ln 3, or ln 3 divided by 2. And then if we multiply and rearrange, that's going to become c equals 2 divided by ln 3. Okay, so we find our value of c, which satisfies the mean value theorem for integrals. Okay, so just to wrap this up, this was a short section, which is pretty easy. We defined the average value of a function on an interval to be 1 over b minus a times the length, 1 over b minus a times the integral of the function. So it's pretty easy to calculate. We said the mean value theorem for integrals says that at some point c, there exists a point c, so the function takes its average value. Okay, so that's everything. So we've wrapped up the final section, and we're now ready to move towards the final exam. So good luck, everyone. I look forward to talking with you more and answering all your questions. So thanks for following the videos, and I wish you the best of luck. Take care.